if you've been watching my previous videos, you've probably got a good understanding now of how we might specify the controls for generating inflation layers. You've probably got a good idea about the first cell height and how we might specify it to achieve a given value of y plus, how we might choose the growth ratio and the number of layers so that we can set the overall height of our inflation layers. But when generating these layers, you may have come across problems with the non-orthogonality or the skewness of some of the cells that are generated in the layers, particularly if you've got a very small first cell height and you're aiming for a y plus of 1. What I want to do in this talk is to take you to the next level of understanding and to show you how layers are actually generated by the CFD code. And we're going to start to look at some of the issues like smoothing and the top cap so that you can understand the problems that occur when layers are generated, and then go back to your meshes and to use this understanding to help improve the quality of your layers. So if you've watched those previous talks, this is going to be a fantastic second part. I know you're going to really enjoy it, and there's going to be some fantastic nuggets of understanding for you in here. Let's get into the talk. Now, before we start, I want to start things off with a small caveat. This talk is only intended to improve your understanding of inflation layers and how they're generated. You can use this understanding to help fix problems with your meshes and improve their quality. Of course, this talk doesn't necessarily represent the actual methods and algorithms that different meshing software actually uses to generate inflation layers. However, the general points that I talk about are going to be sufficient enough for you to understand your meshes and to improve them. So let's start things off by just thinking about a general surface mesh. So you have a surface in your geometry that's covered in a mixture of square and triangular cells, and we would like to generate some layers from this surface. Now, the obvious way that we might think about generating layers from this surface is to use the face normal vector. Now, we're used to the idea of a face normal vector in CFD. All faces in the mesh have a normal vector that's located at the middle of the face and points out of the face. And for generating layers, the obvious thing to do would be to use this normal vector to generate the layers. What we could do is use the direction pointing away from the surface, and then to use that vector to move the face a certain distance, and we could repeat that for all of the faces in the surface mesh, and we could do that step by step, and that would allow us to grow a set of layers normal to the wall in a series of steps that increase in size. Now, that's the obvious method that we might choose to use to generate layers. However, there's a small problem with this approach, and that's what I want to talk about in today's lecture. And the problem, of course, arises if the surface isn't flat. So if the surface has any curvature at all, whether that be concave or convex, what happens immediately if you use the face normal vector that's at the center of the face and use that to project off the surface of the wall? Of course, if the wall isn't perfectly flat, we're either going to get an overlap if we're a concave surface, or we're going to get a gap if we're a convex surface. So this might be the most straightforward method that we use to think about how layers are generated, but of course this isn't actually the method that's used in practice, because there are going to be some problems and we need to fix those problems using some kind of an adjustment. Now, a better way to think about how layers are actually generated is, rather than thinking about the face normal vector, so the normal vector at the center of the face, what the mesh generator does is define a normal vector for each node. So each of the corners of those square or triangular faces on your surface, we define a normal vector for the nodes. And if we project the nodes off the surface rather than the face, that allows us to then have a continuous surface each time we project the nodes to create the next layer, and there are no gaps or overlaps. So this is the key thing for this talk that I want you to be thinking about, is that we're defining the normal vector for the node rather than the face, and using that to project and to create layers off the surface. Now, there are some problems with using nodes to define the layers rather than using the faces. And the first problem I want you to think about is something called warp or warping. And warp or warping might not be something that you've come across before, or you may have seen it raised as a warning or an error in one of your mesh generators. But what does it actually mean? Well, if you think about a quadrilateral surface element, if we define normal vectors for the four corners of the quadrilateral cell and then use those to project the nodes off the surface, we project them up and we generate four new nodes. But of course, those nodes might in practice be moved a different distance, so they might not all necessarily be moved the same distance. And when that happens, the four corners of the new quadrilateral might not necessarily lie in the same plane. I've just given you an example sketch here where these three nodes that you can see at the top have all been projected the same distance, but then for some reason this corner node hasn't been projected the same distance. And that means that we can't define this top face as a single flat surface. It's got some curvature or some warping to it. And that's not good for the CFD code. We would need to correct this somehow with the mesh generator. So this is the first issue that can arise when we're projecting the nodes. The new faces can be warped, and it's not even necessarily the top face. We may have the side faces could be warped, and this is something that the mesh generator will need to account for when it's projecting each time it generates a set of layers. And I just wanted to make a small caveat here, of course, that when you're projecting a triangular face, because you have 3 points only, the top face of that triangular prism can't be warped because those 3 points will always lie on the same plane. And how could we fix the warp? Well, if we think about that first example cell, which I used there, is that perhaps what the mesh generator could do is project those nodes off the wall and then check all of the faces of the cell that's generated. And in this case, we find that the top face is warped, and we could just take that node as a post-processing operation and move it upwards here. And in that case, the top face would no longer be warped and all the faces of the cell would be fine. But of course, this isn't the only way we could fix the warping. We could move one of the other nodes instead. You can think that we could move this top node here downwards instead of moving that bottom node upwards, so that the face would then slope that way, but all four nodes would be in the same plane. And in a similar way, we could move this node instead, in which case the face would be sloping that way instead, but we wouldn't have any warping of the face anymore. But there's a slight subtlety here, which some of you might have picked up on, of course, that if you move this particular node to fix the warp in this face, this node, of course, will be connected to other cells as well. So this node is also connected to this face. It may also be connected to another cell on this side or another cell above it. So while we might be fixing the warp of this particular face, we might be accidentally warping another face when we move this node. So this is why when the mesh generator has to fix warping or other issues with cells, because the nodes are connected to other cells, we have to do this for the entire set of layers as a whole, usually as a smoothing operation. So we're moving the nodes, but to fix the warping in all of the faces simultaneously. So it's not just as simple as moving a node to fix the warp in one cell, because that's going to affect all the other cells around it. And of course, I don't want to go into too much detail in this talk about how a particular mesh generator might be fixing warp or skewness or some other issue. Generally, this is just to give you an idea of how the layers are generated and the problems which may occur along the way, so that you can look at your mesh and to help diagnose problems with it. And of course, this is alluding to warping is not the only problem that can occur when we're projecting these nodes off the surface to generate layers. And we can illustrate this with a very simple example. And I want you to think about a 90-degree corner. So we don't have a flat surface anymore, we've got a 90-degree corner, and we'd like to grow layers off this bottom surface and off the side surface. Now, if we use this same approach that we used before for our understanding, we have the nodes which define the corners of those quadrilateral and triangular surface mesh cells, and we define a normal vector for each of those nodes, and then what we do is just project the nodes off the surface and that allows us to grow our first layer. And so what do we do now? Well, now we need to repeat the process. We take those new nodes for the new corners of the layers we've just generated, define the normal vectors again, and then again project those nodes off the surface of the layers to generate our second set of layers. And you can see that the layer generation process is going to be sequential. You grow one layer at a time, define new normal vectors, then grow the next one, and repeat or loop over the number of layers until you've generated all of your layers. So now we've grown the second layer, let's do it again and generate the third layer. So we've got our set of nodes on the edges of our top set of layers there. We define the normal vectors, and now we'd like to project those nodes off the surface and generate our next set of layers. However, for this example, we've got a problem, and I wonder if you can spot the problem while you're watching this video. Have a pause, stop the video, and think quickly about, with this set of layers, what problem might happen when we try and grow the third set of layers. Of course, what will happen is that if we try and project these nodes off the surface, you can see that the node vectors here are crossing. And what that means is that if we project the nodes and then connect the nodes up to generate the layers, those cells will overlap and they'll be inverted. And this is sometimes why you see something called a negative cell volume or a left-handed face. That cell is inverted. Even though the nodes are connected to each other, they're not connected to each other in a way that leads to a positive volume. And in practice, this means the layer generation process will stop and the meshing process will fail. So this is another issue which can arise when we're generating layers using the normal vector. And this is something which you can even start to observe in your own mesh. If you just look carefully at the layers as they're being generated, you can almost look at your mesh and see, am I in danger of causing those layers to overlap with each other? And one way we could fix this, and you may start to spot this in the examples that we look at later in this talk, one way of fixing this is to, rather than growing the layers using a normal vector that's 90 degrees to the wall, you could actually change the angle of the node vectors instead. So rather than growing this and this vector perfectly normal to the wall, because later up in the layers that ends up with the node vectors crossing and inverting, we could change the angle. And when we do this, we generate again a set of layers, but these layers aren't exactly perpendicular to the wall. But how do we do this in practice? Of course, if you look at the angle of the node vectors themselves, we've got 0 degrees, 45 degrees, 90 degrees, 90 degrees, or for a more complex surface, you could imagine looking at the angle of all of the node vectors along the face of your surface. And when there's a sudden change in the angle of the normal vectors, so hit 0 to 45 to 90, that's indicating that those node vectors are likely to cross as we get higher up in the layers. And of course what we could do is smooth the change in the normal vectors. So here what we've done is change this node vector from 0 degrees to 22 degrees and change this node vector to be 67 degrees rather than 90. And so there's a smoother change in the angle of the normal vectors here. And that will result in a smoother change in the angle of the layers themselves. And so the layers are less likely to cross higher up as we generate them. And that's one way you could use to try and stop the node vectors from crossing. You could smooth the node vectors directly. Or of course the other way you could do it is to just take that top layer of cells and to move the nodes themselves and then to propagate that change lower down through the layers. You could do it that way. And ultimately we may never know what methods the mesh generators actually use to fix these problems, but hopefully for you, when you generate your mesh, you can see if you've got a 90-degree corner or some sharp angles, you can see that a problem might arise where if you grow lots of layers, those node vectors may try and cross towards the top. Now, the second question that I want you to think about here is, as well as those node normal vectors and which direction they're pointing in, I want you to think about how far we should be moving each layer. Because when you set up the parameters for your inflation layers, what you normally set is a first layer height, a growth ratio, and then a number of layers. And so for these layers on the bottom here, it's quite straightforward. We'd grow the first layer and then we'd use the growth ratio to determine the height of the next layer, and then we would just continue that process, and we know exactly how far we would move these nodes as we generate each layer. But that isn't so obvious what we might do for the corner vector here, and that starts to generate some problems, which I'm going to show you in the next few slides. Now, the obvious way of approaching this would be to take the distance that we've just calculated from the parameters that you give the meshing software. So in this example, let's say we chose a first cell height of 1 millimeter. Well, we could use that information and specify each node we're going to move it a distance of 1 millimeter. And you can see here, all of the nodes, we're going to project them in the angle of the normal vector, a distance of 1 millimeter. But immediately from this simple example, you can see that we're starting to get a little problem here. We're moving the nodes the same distance, but if you look at the shape of the top cap of the layers, you can see we're starting to develop a crevice in the corner. Why are we generating a crevice in the corner? Well, if we think about this vector here, it's the distance that we care about. It's how far are we moving the node in the distance of the node vector. And of course, if we're at 90 degrees, that distance is going to be 1. But for the corner, we're moving a distance of 1. And so actually the height of the layer is going to be sine of 45 degrees in this case, which is 0.707. So actually the vertical distance off the wall here, and also the horizontal distance off the wall, is only going to be 0.707. So if we use this approach of moving all of the nodes the distance that's specified in the parameters when you set up the mesh, you can see that you start to develop a crevice in the corner of where the layers are generated. And what's the problem with a crevice? Why do we care about it? Well, if you just look at this corner cell, for example, the corner cell is starting to get skewed already. You can see that this angle here is increasing, and if this was a really tight crevice, that angle would tend towards 180 degrees, which would reduce the quality of the cell. And actually, if we continue this process, so we generate the first layer, these two cells have poor skewness, and we again move a distance of 1 millimeter here, 1 millimeter here, 1 millimeter here, 1 millimeter here, we can see that each time we do this, the crevice actually gets worse. Every time we add more layers, the crevice is getting more and more extreme, and you can see the angle here of this vector, the angle of the corner here is tending towards 180 degrees, which would give us a degenerate cell. So we want to avoid this problem of generating a crevice in the corner. And of course, we may not have a 90-degree corner, we may have an even tighter corner in some geometries for CFD. So what do we do? Well, the easy solution here is when we're projecting the nodes off the surface in the direction of the normal vectors, the trick is to not move all the nodes the same distance. If we actually think of this corner node, and rather than moving it a distance of 1, we could move it a distance of 1 over sine 45, if you think of the right angle triangle, can move it a distance of 1.41, then the second layer here is at the same height off the wall, and we're not generating the crevice here, and you can see that the angle at that corner is much better. So the skewness of these cells are improved. And so in general what that means is that even though when you specify the parameters for your layers, you might be specifying a first cell height of 1, a growth ratio of 1.2 and 7 layers, for example, we're not moving all the nodes the same distance. Some of the nodes may be moved different distances to try and get a good quality of the top cap of the layers. And of course, if you're on a perfectly flat surface, like over here, then those nodes probably will be moved a distance close to that first layer height which you specify. But this uniform height method also has its problems as well. And we thought previously about what would happen if we smooth the node vectors. So rather than having the node vectors at exactly 45 degrees, 90 degrees and 0 degrees to alleviate some of the problems towards the top of the layers, to try and avoid that overlapping, if we change the angles of these vectors, for example, we can see that the uniform height method might not necessarily give us the result we want. So if this corner vector, for example, was at an angle of 60 degrees or 30 degrees, and we projected all the nodes off the surface, you can see that in this case, that angle is going to be increasing towards 150, or if we move this distance here, that angle would be going towards 150 as well, up to 180. So what you want to be thinking about is the ideal set of layers won't necessarily be the exact same shape as the surface. You can see here that in all three examples, the shape of the top cap of the layers is identical to the shape of the surface, but depending on where that projection is, we can still have poor quality cells in the corner. And this is often why, if you look at your layers and if you look at the outer edge of the layers aren't exactly a perfect representation of the surface. There's often some slight change in angle of the top cap, and the vectors aren't necessarily exactly 90 degrees to the wall, because there can be some problems with those cells and we can increase skewness along the way. So what else can we do? What else can we do to this surface? Well, I want you to think back to this simple example here where we've just generated our first set of layers from the wall using a uniform offset distance from the wall. So this length here is greater than 1, this length here is 1. And after we've created that, what we can do is we can do some smoothing on the top cap of the layers. And just looking straight away at this top cap, what you can see we would like to do is we want to do the opposite of what happens when a crevice was being created. So when the crevice was created, this corner was back down here and these nodes were actually further out. Let's think about what happens if we do the opposite. So we take this corner node and we move it out, and we take these nodes and we move them back towards the wall, and we get a shape which looks something like this. So this is what your top cap might look like after the mesh generator has done some smoothing. What's happening here? Well, firstly, if we look at this angle here, we can see that this angle is tending more towards 90 degrees. Of course, if we have a quadrilateral, the ideal cell would be all 90-degree corners. So we've improved the angle of this corner here as well. And actually, we've got further away from the crevice that we had before. We've opened up the angle of the top cap as well. So this is going to help if we want to generate more layers. On the top, we can use the same approach. So we're not going to be tending towards a crevice. So this is generally what you'll see start to happen when the mesh generator smooths the top cap as well, that it will start to take more of an open shape rather than a closed crevice. And what this improved top cap also does, of course, is eventually when our layers are finished, we'll want to be growing pyramids or tetrahedral cells on the top to blend into our volume mesh. And of course, as this corner angle closes down into a crevice, it's more and more difficult to generate tetrahedra or pyramids in that corner because there's less space for us to move the apex around. Whereas when we start to open up that corner, there's more distance that we have to play with when we move around the top of the pyramid or the tetrahedra. So you can see that this kind of shape is generally really, really good for the top cap of our cells because we've reduced the skewness of these corner angles here, and we've got more room to play with for our tetrahedra and our pyramids that we grow from the top. Now, there's one problem with this approach which some of you may have noticed, and is actually something that often crops up when you do generate these meshes for real, and I'm hoping that this bit will really help to explain and to help you fix some of the problems with your meshes. I want you to imagine that we've got a set of 4 layers, for example, like this, and the mesh generator has created the layers and has then decided to smooth the layers using the examples we saw before. You can see that the top cap has been opened up, so we're moving away from a crevice more towards an open concave shape. So we've smoothed the layers. That'll be nice and easy for the mesh generator to fit tetrahedra and pyramids in there. And we've also changed the angles of the normal vectors here so that we aren't changing from 0 degrees to 45 degrees to 90 degrees. So you can see the layers are at an angle. Now, the problem with this approach often occurs when you have a very thin first layer height. So if you have a mesh where you're aiming for y plus of 1, a lot of layers, maybe you're aiming for 15, 20 or 30 layers, you've got a deep set of layers and that first layer is really, really thin. It might be 0.1 millimeters, it may be even thinner depending on your Reynolds number. And of course that very thin cell right at the bottom, you may have noticed that often the thinnest cells which are closest to the wall, these are the ones which often cause the problem for the mesh quality metrics. Obviously they're going to have a high aspect ratio because they're very thin, they're always going to have a high aspect ratio, but small changes in the angle of the side edges, which you can see here, can significantly increase the non-orthogonality of those cells. And this is why the cells which are right on the wall of the mesh are often the ones which cause problems for the quality metrics and ultimately for the solution of the meshing problem. Now, that won't be a problem for our original mesh because, of course, these layers at the bottom, even though they're very thin and they will always be very thin because we've specified a very thin first layer height, that normal vector is at 90 degrees exactly to the wall. So the non-orthogonality won't be an issue because if we draw our vector between the centroid across the face to the other centroid, that vector is perfectly orthogonal to the face, and so these cells here won't be a problem for non-orthogonality. This cell, of course, in the corner may be because of the angle here, but the original mesh won't cause a problem for the non-orthogonality, but the smoothed version might do. So you can see that there are some competing issues here with the mesh. And what's the solution? What's the solution? How do the mesh generators get about this? Well, the trick is to use a mixed approach. And how does the mixed approach work? Well, if we take that bottom layer, so the very bottom layer, and we use an orthogonal approach for the bottom layer, so all of those cells, the node vector is exactly at 90 degrees to the wall, so we won't get any orthogonality problems in the bottom layer. And then for the layers above it, we allow the node vector to move, we allow the mesh generator to use a smoothing approach for the top cap. So then by the time we get to the top of the layers, we have that nice open corner. And these cells here, the skewness is improved. You can see that angle is actually getting quite close to 90 degrees. And if you zoom in on the mesh, you'll see that the node edge would look something like this. So we've got the first layer is orthogonal, and then the outer layers are actually still at an angle. And of course, this will decrease the non-orthogonality of these layers, but because these layers are now a lot thicker, because we've grown further from the surface, they're less likely to cause problems for the quality metrics. So this is the mixed approach, and you can see it's getting the best of both worlds. And of course, we aren't limited to just using orthogonal layers for the bottom layer. We could take the first 2 layers, the first 3 or the first 4, and we could continue to use orthogonal layers and improve the quality of those cells further from the wall. And effectively what this is doing is shifting the problem further away from the wall. So we could use 2 layers, 3 or 4. And if you now think about the zoom in on the mesh, how that looks, you can see that now we have the 2 layers which are orthogonal, but then the third layer, the outer layers, those node vectors are allowed to move at an angle. But of course these cells are much thicker now, and so this is less likely to cause quality issues for the non-orthogonality. And in practice, there's likely to be an optimum number of orthogonal layers, which some mesh generators will find in the background as they're smoothing the layers. They'll do this for you, and other times you may be able to specify the number of orthogonal layers yourself, and you can just try and improve. You can try with 1 layer, with 2, with 3, with 4, and you can look at the quality of the layers and see which set of controls actually gives you the highest quality mesh. But this does lead us to an apparent contradiction. If we think about what we said earlier, the orthogonal layers approach gave us problems because the node vectors can overlap, and of course that would lead us to an inverted cell, a left-handed cell, and the layer generation would fail. So why have I contradicted myself? Why have I said at the start you shouldn't use an orthogonal layers approach, and now I've said, oh, a mixed approach is great and that's actually the way forward and you should use orthogonal layers. What's the key here? Well, the key observation here, which I've been subtly alluding to throughout the talk, is that the bottom layers are very thin. So even though we've used an orthogonal layers approach, these layers are actually very thin. So we're only moving a small distance in the direction of the node vectors. So that means for those layers that are very close to the wall, they're highly unlikely to overlap. And you can even see that here just from the example. If we grew another layer that was orthogonal, those layers aren't going to overlap because the distance we're moving is very small. But when we're further away from the wall, our layers are larger. When we move that big distance in the direction of the normal vectors, we're more likely for our node vectors to overlap. And this is exactly why we're able to use this mixed approach of orthogonal layers close to the wall and then smoothing and moving the node vectors further away from the wall to give us the best of both worlds. Now, here's just a quick example from a typical mesh of a 90-degree corner which I created, and I'd encourage you to do the same as well. Have a look at your mesh and look really closely at those layers close to the wall and see if you can spot what's actually happening. Now, for this particular example, if you follow the line here out from the outer layer where we've got the pyramids and the tetrahedral cells here, if you follow the line of the layers back through the thickness, you can see that these layers, of course, have been smoothed and the node vector is at an angle. But if you follow the line, once you get close to the wall, you can see that that angle changes and these layers close to the wall are actually orthogonal. You can see the layers are initially orthogonal, and then when they're far enough out, the mesh generator with its smoothing realizes that we can now start to smooth the layers without affecting the orthogonality, and the node vector continues at an angle. So this is the mixed approach, and I'd really like you to have a look at your mesh and see, can you spot the orthogonal layers close to the wall, or are those layers thick enough that the mesh generator is just generating those layers at an angle all the way to the wall? And the final thing you can spot in this example is actually the angle of that corner, which I spoke about earlier. Remember, we don't want to be generating crevices in the corner, we want to open up that angle as much as possible. And you can see just from this diagram here, this image here, that angle actually isn't 90 degrees, it's larger than 90 degrees. The mesh generator has opened up, and so it's a lot easier for it to fit the tetrahedra and the pyramids in that particular corner. And the shape of the top cap, if you follow this line, it's not a perfect 90-degree angle with straight lines. You can see it's actually a curved surface here that comes in towards the corner to open up the angle and then extends as we go away. And indeed, if you went further down the wall, eventually you'd find all the layers are exactly orthogonal to the wall, and the top cap would be an exact representation of the wall itself. So those are some little observations. I'd highly encourage you, open up your meshes that you've already created or have created in the past and zoom in your corners very close to the wall and see if you can see what the mesh generator is doing. So, quick summary to wrap up the talk. The layers are grown using the node vectors and not the face area vectors. And the reason for that is we want to be able to avoid gaps and overlaps in the layers that occur when we have a concave or a convex surface. And the key with the node vectors is that if they overlap, that will generate an inverted or a left-handed cell and the layer generation will fail. And so that means the mesh generator has to use different approaches to avoid the node vectors overlapping. And a very efficient way of doing this is to use orthogonal layers close to the wall to improve the quality of those cells. And because the distance that those nodes are being moved each time we generate a layer is very small, we're highly unlikely for the node vectors to overlap. And then further away from the wall, the mesh generator will use some type of smoothing which changes the angle of those node vectors and opens up corners so that we can improve the top cap and stop the node vectors from overlapping. So that brings me to the end of the video. I'm really enjoying this new series of lectures that I'm making on meshing, and I hope that they're really helping you to improve your understanding of meshes and the problems that can be caused during the mesh generation process, and how you can use this understanding to improve your meshes that you've got and ultimately get better CFD solutions. So let me know in the comment section, are you enjoying the videos? And if you are, share them with a friend who might benefit from some of this additional understanding and help them if they're struggling with the meshes that they're generating too. That would really mean a lot to me, knowing that everyone is helping to improve their meshes, and so we can all get better and more efficient CFD solutions. Thank you all for continuing to support the channel. I really appreciate it, and I'll see you in the next video.